a mysterious interstellar object has shaken both the scientific community and the public in recent times. 3I Atlas. Unlike the ordinary comets we've known before, 3I Atlas carries within it mysteries humanity has never touched. By the end of October 2025, it revealed a series of astonishing phenomena. Its brightness erupted unexpectedly, far surpassing every conventional prediction. This left astronomers genuinely stunned. What's even more remarkable is the strange blue light emitted from 3I Atlas. Along with that came evidence of the presence of atomic nickel, a chemical element that raises confusion and deep questions. These elements have led to a startling question. What exactly is 3I Atlas? The mysteries 3I Atlas brings not only draw the attention of scientists, but also ignite the curiosity of people around the world. Together, let's dive deeper into this phenomenon and explore the wonders it may reveal about the vast universe we live in. As humanity continued to track 3I Atlas, the third confirmed interstellar visitor ever observed, something seemingly coincidental was unfolding at the very center of our solar system. The Sun was entering the energetic peak of its 25th activity cycle. That coincidence opened an entirely new chapter in the story of this mysterious object. Imagine this. On one side, an ancient, solitary block of ice drifting through the cold vacuum of interstellar space for billions of years. On the other, our star, erupting violently with waves of plasma, X-rays, and ultraviolet storms. When these two worlds, ice and fire, stillness and motion collide, what happens? Solar monitoring satellites revealed that between September and October 2025, the Sun released several X-class flares, the strongest of its current cycle. At precisely the same time, telescopes recorded a sudden and dramatic brightening of 3I Atlas, far beyond any prediction, a phenomenon that no existing cometary model could explain. The nucleus of 3I Atlas is believed to contain frozen methane, ammonia, and carbon monoxide, compounds common among ancient comets. Yet instead of gradually sublimating like typical comets, it appeared to be awakened by a surge of high-energy radiation, causing the ice to vaporize almost instantly. Electrically charged particles were expelled, forming a dual-ion tail stretching over 30 million kilometers, a measurement that left scientists astonished. Spectroscopic analysis from the James Webb Space Telescope and ground-based observatories like the Very Large Telescope revealed that the ratio of carbon dioxide to water in the coma of 3I Atlas was extraordinarily high, far beyond any known comet within our solar system. Moreover, the outflowing gas contained traces of neutral atomic nickel, an exceedingly rare phenomenon only previously detected in a few massive comets like 2I Borisov. This finding suggests that 3I Atlas contains material formed under entirely different conditions of temperature and pressure, possibly within a metal-rich nebula, unlike the one in which our Sun was born. Measurements also showed a striking correlation as solar ultraviolet intensity increased. Within mere hours, the brightness and ion tail length of 3I Atlas surged dramatically. This behavior was drastically different from normal comets, which usually respond far more slowly to solar energy fluctuations. Was this merely a coincidence, or evidence of a complex electromagnetic reaction never before recorded? Some plasma physicists propose that high-energy solar radiation may have triggered electrochemical reactions within 3I Atlas's interstellar material, producing a cascade of ionization and re-emission visible as light. Another theory suggests its core may contain metallic conductive compounds, making it extremely responsive to the Sun's magnetic field, essentially functioning like a colossal cosmic antenna that absorbs and retransmits stellar energy. From a scientific standpoint, this data opens two remarkable pathways for exploration. First, interstellar matter may have a chemically distinct composition compared to the material formed within our solar system, offering a new understanding of the diversity of star-forming nebulae across the Milky Way. Second, the interaction between interstellar objects and stellar environments may be far stronger than we've imagined, perhaps even the key to unlocking how energy transfers through cosmic plasma, one of the great unsolved mysteries of space physics. So, is 3I Atlas merely reacting through physical processes, or revealing properties of matter that exceed our current scientific understanding? Observatories around the world, from the European Space Agency to the Rubin Observatory in Chile, are now racing to capture every photon reflected from this wandering traveler. Because once it drifts beyond the Sun's influence, the chance to study it directly will be lost forever. As 3I Atlas continues its journey out of the solar system, it carries with it not just ancient ice and dust, but also questions far greater than itself. How many other objects like it roam the void, bearing remnants of long-dead stars? And perhaps, in witnessing this fierce exchange between light and darkness, are we glimpsing a deeper secret of the universe itself, where energy, matter, and time intertwine in one vast cosmic experiment? While most telescopes on Earth were still focused on observing the violent outburst of 3I Atlas, another, less publicized discovery began to emerge from orbital data, one far more unsettling. The encounter between this interstellar visitor and the Sun was shaking the astronomical community, not just because of its brilliance, but because of how it moved. 3I Atlas, it seemed, was refusing to obey the familiar laws of gravity that we've long trusted. at the National Astronomical Observatories of China and several international orbital dynamics centers, simulations based on Newtonian mechanics and the gravitational effects of major planets all produced smooth, predictable trajectories until real data was introduced. The actual orbit of 3I Atlas deviated by about 0.07 degrees from theoretical models. That may sound small, but on a cosmic scale, it represents a shift of millions of kilometers. More importantly, this deviation was stable, directional, and could not be explained by measurement error. This phenomenon is known as non-gravitational acceleration, a force not caused by gravity but by internal or external interactions. In ordinary comets, such acceleration usually comes from uneven outgassing, as jets of vapor push the body in tiny bursts. But in the case of 3I Atlas, the observed acceleration was far too strong to be explained by sublimation alone. Something else was at work. Three main hypotheses have been proposed, and each opens an even deeper mystery. The first suggests asymmetric sublimation recoil. An unevenly evaporating comet can, in theory, push itself off its expected orbit. However, spectral data showed that the amount of gas and dust released by 3I Atlas was insufficient to generate the measured acceleration. Simple outgassing does not explain the anomaly. The second focuses on the influence of solar plasma storms. 3I Atlas passed the Sun precisely as it reached the peak of solar cycle 25, a period when solar plasma winds, ultraviolet bursts, and high-energy protons surge at their most violent levels in over a decade. Some plasma physicists propose that the ionized haze surrounding 3I Atlas acted like a natural plasma sail, absorbing solar energy and being deflected by streams of charged particles from the Sun. While this model fits part of the data, it still falls short. The plasma density required to produce such force is far higher than what was actually observed. This leaves open the most controversial hypothesis of all: electromagnetic interaction with a conductive structure. Spectroscopic observations from the James Webb Space Telescope detected traces of free atomic nickel within the gas ejected from 3I Atlas, a form of matter rarely seen in natural comets, typically found in environments that form around other stars. If its core contains a high concentration of conductive materials or complex metallic compounds, then as it passed through the Sun's powerful magnetic field and dense plasma streams, 3I Atlas could have been subjected to Lorentz forces, producing a genuine electromagnetic acceleration. This would not be mere physics as usual, but rather an energy interaction mechanism never before witnessed in any comet, a form of propulsion unlike anything observed in nature. For this reason, several astronomers, including Professor Avi Loeb of Harvard University, have publicly raised the question, Can 3I Atlas be such an extraordinary natural structure that it mimics artificial propulsion? Or is there something else behind it? He emphasized, however, that this remains purely an exploratory hypothesis. Most major institutions, including NASA and JPL, continue to take a cautious stance. There is no evidence requiring us to abandon the framework of natural physics, but 3I Atlas is challenging every model we thought we understood. Now, as the object drifts away from the solar system, disappearing into the cold, dark expanse where telescopes can barely follow, one question remains, suspended in the silence of space. Is this non-gravitational force simply a natural mechanism we have yet to comprehend? Or is it a signal of a new physical principle? A hidden language of energy that the universe is quietly trying to reveal to us. As we conclude our analysis of the strange orbital deviation of 3I Atlas, where standard gravitational physics seems no longer sufficient to explain its motion, a larger question has begun to emerge, not from a fringe group of theorists, but from one of the most recognized scientists in the field, Avi Loeb of Harvard University. While many experts continue trying to attribute the object's non-gravitational acceleration to natural processes, Loeb stares directly into the anomaly and asks one of the boldest questions in modern astronomy. Is 3 Atlas merely an inert block of cosmic ice and rock, or could it be a guided object? A technology deliberately hidden among the stars. Loeb argues that 3I Atlas stands at a fragile boundary between the natural and the engineered. One of the key characteristics he points to is its nonlinear variation in brightness. He writes that if an object were freely rotating in space, its apparent brightness would shift in a nearly periodic pattern, matching its spin and the way it reflects sunlight. Yet observations show that 3I Atlas behaves differently. Its light fluctuates irregularly, unpredictably, and in no pattern ever recorded in a typical comet. He suggests that such behavior could originate from an artificially structured reflective surface. Perhaps a kind of outer shell or engineered layer designed to scatter sunlight intentionally or through a specialized composition. Loeb notes that in ordinary comets, ice and dust reflect sunlight randomly. But if the reflective surface is controlled or shaped by design, then the pattern of reflected light would no longer follow simple rotational dynamics. And this is where the ghost of Oumuamua, the first interstellar object discovered in 2017, reappears. Loeb once proposed that Oumuamua might have been a light sail or extraterrestrial probe. Now, he warns that 3I Atlas could be a larger, more complex version. In the object deliberately engineered to hide among the natural population of comets and asteroids. To test this idea, Loeb has proposed a direct approach, using the James Webb Space Telescope with its powerful infrared spectrograph to determine the reflective composition of 3I Atlas's surface. Specifically, he seeks to know whether it is made purely of ice and silicates, like normal comets, or if it contains signatures of pure metallic elements, or composite materials capable of surviving billions of years in interstellar space, substances that only advanced technology could produce. Meanwhile, NASA's Jet Propulsion Laboratory, known as JPL, remains far more cautious. Their position is clear: there is no direct evidence that 3I Atlas is artificial. Yet, they admit with equal clarity: the orbit and behavior of this object are truly anomalous, beyond most of what our cometary models can account for. That admission alone has split the scientific community into two distinct camps. The conservative camp, including JPL and most major space agencies, maintains that 3I Atlas is an extraordinarily rare natural body, carrying interstellar material never before studied. They argue that its strange behavior could still be explained by known physical processes: outgassing, solar radiation, or plasma interactions. Though under extreme and unusual conditions, the progressive camp, led by Loeb, contends that if the orbital anomalies, nonlinear brightness, and abnormal metallic composition continue to exceed all error margins and theoretical limits, then science must at least consider the possibility that this is the relic of an ancient technology, or even a probe from another civilization. At that point, astronomy would no longer be just observation. It would become an invitation to action. A call to courage, to ask bigger questions, to challenge the boundaries of what we believe nature can do. And so, within the astronomical community, emotions are now mixed. Wonder entangled with skepticism, fascination wrestling with fear. Because if 3I Atlas is merely a natural wanderer carrying the dust of forgotten stars, that alone would be a monumental discovery, ushering in a new era of hands-on research into interstellar material. But if it is more than that, if it represents the first trace of alien technology, then we are standing on the edge of a profound turning point in human understanding of our place in the cosmos, of our potential to communicate, and of our readiness to face the unknown. And now, for those watching from Earth, one haunting question still echoes through the vast silence of space. When a traveler from between the stars knocks on the door of our solar system, will we simply watch, or will we look closer, listen deeper, and truly pay attention? Because with 3I Atlas, it is not just about how it arrived or how it moves, but about how it reacts and interacts. Perhaps revealing the greatest story ever told about both the universe and ourselves. When the first data from 3I Atlas was released, the global scientific community's attention quickly shifted from curiosity to cautious alert. This was only the third interstellar object in human history ever observed passing through our solar system. After Oumuamua in 2017 and Borisov in 2019. That meant every measurement, every observation carried a singular importance, because there would never be a second chance to study this same object again. According to astronomical projections. Atlas would reach its perihelion, the point closest to the Sun, at roughly 1.4 astronomical units, in the weeks leading up to that moment, NASA, ESA, and observatories across China, Japan, and South Africa simultaneously increased their monitoring frequency. Sharing real-time data through the Minor Planet Center International Network. At NASA's Goddard Space Flight Center, an emergency internal meeting was convened, bringing together teams from JPL, the Harvard-Smithsonian Center for Astrophysics, and the Ames Research Center. The objective was clear: to evaluate strategies for tracking 3 atlas. And assess whether a rapid response observation mission could be initiated using existing infrastructure. Rather than waiting years for a new probe launch. Scientists agreed that the window of opportunity was vanishingly brief. The object's relative velocity exceeded 75 kilometers per second. Meaning that with every passing second, it was distancing itself from Earth by tens of thousands of kilometers. Without an active probe positioned along a favorable trajectory. A close flyby was physically impossible. Thus, instead of discussing new spacecraft, the meeting focused on maximizing remote observation, particularly through the James Webb Space Telescope, Hubble NEOWISE. And ground-based telescopes in Hawaii, Chile, and South Africa. NASA also collaborated with ESA to incorporate spectrographic data from Solar Orbiter and Solar Cruiser, aiming to monitor how 3I Atlas reflected sunlight and how its material emission changed as it approached the Sun. Though there was no direct evidence of artificial behavior. The irregular light reflection from 3I Atlas led several research groups to suspect that its surface was not entirely chaotic like a typical comet's. Instead, it might contain directional reflective materials, a feature that had stirred similar debate during the 2017 study of Oumuamua. When JWST turned its instruments toward 3I Atlas, the spectroscopic data surprised even the most seasoned researchers. The ratio of carbon dioxide to water vapor in its coma was several times higher than that of any known inter-system comet. While NASA maintained a cautious stance, independent scientists, including Professor Avi Loeb of Harvard University, argued that the optical and dynamic properties of 3I Atlas warranted investigation under non-natural hypotheses, not as a declaration of artificial origin, but as a way to expand the boundaries of scientific reasoning. However, most experts from ESA, CNES, and JPL reaffirmed that there was no evidence supporting the idea that 3I Atlas was an artificial object. The debate ignited intense public interest, and though NASA made no official comment, it quietly reallocated observation resources. Elevating 3I Atlas to one of its top priorities of 2025. Determined not to repeat the oversight that nearly caused humanity to miss its chance with Oumuamua. As 3I Atlas passed perihelion and began drifting out of the solar system toward the constellation Hercules, telescopes worldwide rushed to capture every last photon of light. With each passing hour, its glow dimmed. Every lost data point became a permanent, unrecoverable moment. NASA described 3I Atlas as a messenger from other stars. An ancient signal sweeping briefly through our sky. Carrying within it possible answers to the origins of distant worlds. And if we're quick enough, curious enough, and persistent enough to understand, then the passage of 3I Atlas will be more than just an astronomical event. It will be a test of humanity's deepest desire to explore. As the three major space agencies, NASA, ESA, and CNSA, prepared for decisive steps to observe and study the interstellar object 3I Atlas. Their curiosity extended beyond how it moves or what it is. They wanted to understand what it is made of and where it came from. Because 3I Atlas may hold traces of the universe's distant past. And through it, we might follow the faint chemical footprints of a place far beyond our own solar system. Recent observations reveal that the composition and internal structure of 3I Atlas are remarkably distinct. Using the James Webb Space Telescope's infrared spectroscopy and ground-based observatories to analyze the coma, the thin atmosphere of gas, ice, and dust surrounding its nucleus. Scientists began to uncover a chemical and physical map unlike that of any comet known within our solar system. One of the most striking findings is the ratio of carbon dioxide to water. Measured among the highest ever recorded in any comet. This suggests that the object's core either contains or was formed by an abundance of carbon dioxide ice, or that it underwent a unique evolutionary process in which water was either depleted or trapped deep within. Furthermore, isotopic analyses revealed that the ratio of nitrogen-15 in the gases escaping from 3I Atlas is abnormally high, far exceeding that found in most inner solar system bodies. This distinction is considered an interstellar signature. Because when an object forms in a stellar system different from our own, its isotopic composition carries a unique fingerprint shaped by the star's evolution and the local chemical environment where it was born. Based on these findings, models developed at major research institutes proposed two possible origins for 3I Atlas. It may have once been a fragment ejected from its parent system by one of two mechanisms. The first scenario suggests it was ejected from its parent system during a supernova explosion, which blasted away its outer layers and hurled fragments into interstellar space at extreme velocity. The second posits that it was gravitationally expelled during the early chaotic phase of its star system. Perhaps slingshotted by a massive gas giant or a powerful gravitational encounter, during its journey through the interstellar void. 3I Atlas was continuously bombarded by cosmic radiation and high-energy charged particles. A recent study based on observational data suggests that its outer shell has been chemically altered by this exposure, forming a carbonized crust and changing the composition of its emitted gases and ices. This means that what we are observing today may not be the pristine material it was born from. But rather matter reshaped by the harsh environment of deep space. If the outer layer of 3I Atlas has been irradiated, and its outgassing dominated by carbon dioxide and conductive metallic elements, then does its core still preserve the original material from its formation epoch? And can we ever access that ancient nucleus before the object escapes the solar system forever? Otherwise, we may only be witnessing the altered exterior of a cosmic time capsule. Without ever touching its true origin. Another fascinating component is water. Although many observations confirmed an unusually high level of carbon dioxide. Ultraviolet measurements from space-based telescopes also detected the presence of hydroxyl byproduct of water decomposition, escaping from 3I Atlas at distances far greater than those typical for comets. This implies that its water ice may be shielded or deeply insulated. Or perhaps sealed beneath a radiation-hardened crust. allowing it to vent only under specific thermal conditions. Soon, 3I atlets will depart the solar system, vanishing from direct observation forever. This reality creates a tense race against time. Every spectrum captured, every data point on composition or dynamics carries monumental value. For they may be the only evidence humanity will ever have of direct contact with material born from another star. After its sudden brightening, mysterious orbital deviation, and a series of global emergency meetings, the object is expected to move beyond the range of effective observation by the end of 2026. Continuing its hyperbolic trajectory into deep space. From its unusual chemical composition, anomalous isotope ratios, to the interstellar radiation scars etched across its surface, every piece of data points to a single truth. This object does not belong to the solar system. It stands as proof that the universe is not isolated. That matter itself can travel across billions of light years to reach us. What 3I Atlas offers is more than scientific data. It is a reminder of humanity's place within the grander tapestry of the cosmos. In the brief moment it passed by, we were granted a rare glimpse of material born in another world. A chance to touch the remnants of stars that died long before our own sun was born. As the final light of 3I Atlas fades into the cosmic horizon. It leaves behind a quiet yet profound question. How many others like it are still wandering out there, carrying the stories of distant star systems? And perhaps somewhere else is someone looking back toward us, wondering the very same thing? Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.